Okay, so this lecture is on confidence intervals and hypothesis testing. Now, there's easy marks in both of these sections here. You've just got to follow protocol. So your confidence interval is you've got two formulas, and your answer is obviously going to be an interval. So it's a lower boundary and an upper boundary. If it's asked in a forwards way, all right. We've got Z scores, and then we're gonna fill in all the information they've given us. Okay. So a random sample of 64 completion times for a task gave a sample mean of 35 seconds and a sample standard deviation of 16 seconds. What is a 99% confidence interval for the population mean completion time? So what this is saying is, a 99% is very confident. So basically, my interval is going to be a bit bigger, a bit wider than, let's say, a 90% confidence interval, because there's a 99% chance that the true population mean would be within my interval. And that's what you are basically working out. So basically, your interval, the confidence interval, is always going to be in the middle, all right? Which means you've got a lower boundary and you've got an upper boundary. It's like a two-tailed hypothesis test. All right, so let's look at what we would do. So if you've got a 99% confidence interval, to get our Z score, we want to split it into half of it, so we can find out from 0 through to there. So this is going to be 0.495, which is because I know that 1% has to be on either side, so 0.05% needs to be on each side. Okay, so once I've got my 0.495, I want to find out my Z scores, and then I'm going to put it into my formula. So my mu equals the sample mean, always a sample mean, plus my Z times by my standard deviation over the root of n. So my interval is between 29.8 and 40.2-ish. So what does it mean? It's a 99% confidence interval that the completion time is between 29.8. In other words, I'm 99% sure that the true completion time would be between that value and that value. Now, this interval is fairly wide, 29.8 and 40.1. So it is fair to be 99% confident. Okay, so let's have a look at the next example. So this one is an example of proportion type questions. So when you get a proportion type question, your first thing you're going to do is work out what your p hat will be. So in this case, our p hat is 220 divided by 500. Okay. Then we want to figure out what our Z score is. So we want to split this in half, and we realize this is going to be 0.45. So our Z score is going to be 1.645. So to work out our solution, we're going to go 0.44 plus or minus, and we're going to work out the solution. Okay, so we're going to get an interval of 0.4 to 0.48-ish or so, and we are 90% confident. So that's not such a big interval for what the data that we're dealing with is. It's a 90% confidence interval. So we're 90% sure that the true proportion lies between that value and that value. Okay, so let's look at some different type of questions on this. So a die is biased so that the probability that it shows a 6 on any throw is p. In an experiment, the die shows a 6 on 22 out of 100 throws. Find a 97% confidence interval for p. Okay, so we know our p hat is going to be 22 out of 100. We've got a halfway point, 97 is 0.485, and a Z score of 2.17. So we can put this in, and that's pretty easy, and I'm going to get a nice interval, which is 0.13 to 0.31. Okay, so the second question goes, the experiment is repeated, and another 97% confidence interval is found. All right. Find the probability that exactly one of the two confidence intervals includes the true value of p. Okay, so basically what we've just worked out here is that 90% is a 97% chance that the true value of p falls between these two values over here. So what is our solution is, if we do another 97% confidence interval, there's a 3% chance that it doesn't fall within that. All right. So What are they saying? Exactly one of the two confidence intervals includes a true proportion. So that would be it. In the first go, it does, 97% chance, and the second go, it doesn't, so 3% chance. Or it doesn't in the first, 0.03, and it does in the second, and that's why it's times by 2. So basically, it's just dealing with probability and trying to confuse you because you've just worked out that. Okay, so maybe it needs a bit of thought, but think about it. 97%, remember, is your probability. So what's the probability of success is 0.97. What's the probability of failure is 0.03. So you could even do a binomial. All right. All right. If we take something like this, this is often sort of asked. If that is asked, you're very lucky, and it's nice, easy marks. The mean weight of 25 female lab dogs is in the interval 25 to 32 kilograms with a 94% confidence. Find the sample mean and the standard deviation. Okay, so we're looking at obviously this formula here, and the sample mean is always easy because as soon as they've given us the interval, we want to add these two and divide by 2 because my sample mean is slap bang in the middle of those. So it's 28.5. Okay, so we want to now find the standard deviation. So we've got this x bar. So we need to find out, we've got n, so we need to actually find our z score. Okay, so we're looking at a 94% confidence interval. So my half point is 0.47 and my z score comes out to be 1.88. Okay, so now I can fill in all the different values and try and find my sigma. Now in my muse position here, I'm actually going to put my upper boundary because I'm going to use the x plus my z score. So watch, I've got 32 in the upper boundary place, and then I've got my x bar, which is what I worked out there, plus my z score, and I'm going to now find out what my sigma is. Okay, if I wanted to use 25, my lower boundary, then I need to use the minus sign for the z in front of the z. Okay, so let's have a look at these two types of questions here. Sample states that 10% of people are left-handed. Okay, what size sample should you choose to be 96% confident that the true proportion is within 2% of the sample proportion? Okay, so this type of question, if we take our proportion formula, all right, basically they're asking us what size sample should you choose so that this part over here, right, is within 2% of the sample proportion. So that is within 2%. So what are we going to do is we're actually just going to make that within 2%. So I'm going to find my Z score, the 96% confidence, and I'm going to chuck it all in and I'm going to solve for N so that that is within my 2%. Because I'm taking a proportion and I'm adding and subtracting basically a proportion. All right, so N comes out to be 946. The other type of question is they say to you, let's say, find a 96% confidence interval is constructed. The width of this confidence is 0.1. Find N. So they've given you the width of the whole confidence interval. So from lower boundary to upper boundary. So again, we've got a Z score. We just deal with this part again, but this time we're going to say half the boundary because this would be just the half if we're just using the Z times by that. So that would be half of 0.1, which is 0.05, and I'd solve for N, so it's 151. Okay, but both times they're asking you to just deal with this part. Okay. Okay, so this question now is clearly, if you have a look through it, you're looking for whether it's confidence intervals or what, all right? So the length of rods produced in a factory is supposed to be blah, blah, blah. The managers claim that one machine, as soon as we start looking at claims, a random sample of 40 tests the claim at a 2% significance level. This is now, we are definitely heading into hypothesis testing, and this is great, easy marks, guys. Okay, so Where do we lose our marks? Our markers section every year, and where these guys end up losing marks is in your first statement. You have to, first of all, go H0, which is your null hypothesis, and you're always dealing with the mu here. It has to be a Greek letter. Okay, if it's X bar, you don't understand and you lose every last little bit of marks. Okay, so first thing we're going to say is what is it supposed to be? Okay, so in other words, we don't want to look at our claim. We don't want to look at what we tested. We don't want to look at a sample. We want to look at the length of rods is supposed to be 250. What is our claim? Is the person random sample of 40 is taken and the mean length is found to be 250. Test the claim at a 2% significance level. Manager claims that is producing rods on average that are too long. So we want to say bigger than 250. These values have to be the same. Okay. Right. Once you've done that, we're going to look at what our critical values are. So we want to look at our 2%. Now, because this is bigger than 250, it means it's one-tailed, which means my full 2% has to be on the one side. All right, it's bigger than, so it's on this side. So what am I looking for is my 0.5 minus that so that I can find a z-score. I look it up, and my z-score comes out to be 205. Okay, that z-score is my critical value. I want to compare everything against that z-score. So now I go and I run a test. Okay, and I use the test statistic, this formula Z equals X bar minus the mean of the standard deviation over the root of N. So that X over there has to be what we are testing, okay? That is our sample mean. So we're going to put that in, we get a value of 1.9. What am I doing with that 1.9 is I'm comparing it to this number over here. Okay, so where does 1.9 lie? It's less than 2.05. So therefore, it's in this section over here. And in this section over here, we say that there is not enough evidence to reject the null hypothesis. Okay, so at a 2% level of significance and suggest insufficient evidence to support the claim. Okay, because it isn't outside of the ordinary. Okay, so that's basic, absolutely normal. No reason why you shouldn't get one of these. Okay. Okay, let's look at a different question. So a street vendor sells fruit on the corner of two main intersections. He collected data about his sales in the summer months and the winter months. He chose 5 weeks in summer and 5 weeks in winter. Okay, so this is looking like comparing two different sets of data. He found that he has sold an average of 68.2 items in the 5 summer weeks and 52.8. Yes, definitely. We're definitely looking at two sets of data. Set up a formal hypothesis test at the 6% significance level to test his claim that his sales have differed by at least 5 items from winter to summer. Okay, so he's actually giving it even a value, given that the standard deviation is 6 and winter is 7, and the items sold follow a normal distribution. Okay, so we're going to let x equal the summer and y equal the winter. All right, so what have we got here? So the null hypothesis is saying that the summer is equal to the winter plus 5 weeks. Okay, or mu x minus mu y equals 5. Okay, what is the claim? That mu x doesn't equal mu y plus 5. Okay, in fact, mu x minus mu y is not equal to 5. So I could change the subject to the formula to make it suit what I want to say. Okay, now I want to put in my different values. I know this is two-tailed test. Okay, why is it two-tailed? It's because the test says that they have differed, not that the one is bigger than the other. Okay, so two-tailed means I share my full 6% on either side. So this value over here is 0.47, and it means my z-score is 1.88. Test statistic is the other formula, so I'm going to go 68.2 minus 52.8 minus my mu x minus mu y, which is 5. Fill in my values and I get my test statistic. Now what am I saying is this value over here compared to that is bigger. So what does that mean now? It means that we can reject the null hypothesis at a 6% level of significance and suggest sufficient evidence to support the claim. Okay, so those are the two different types of hypothesis testing. Practice, practice, practice. They're always worth about 10 or 11 marks, and they're always so easy, all right? If you have any questions on it, please feel free to ask. This is the biggest error, and this gives you no marks, okay? So when stating the null and alternate hypothesis, you cannot compare sample mean with a sample mean. So if you say X bar and X bar, you get nothing, okay? That is completely and totally wrong, wrong, wrong. It has to be Greek letter, Greek letter. Okay.